Okay, any other questions about anything right now before we jump into Unit 3? And I apologize again for the little bit of overlap. Once again, just because of lost time. Normally this won't happen where we start a unit before we've actually tested on the previous one. But it's just the way life is right now, so we just do the best we can with that. Okay, 3 smiley faces to get us started off today. You can talk to your table buddy if you'd like. I'd like you to draw me a picture at the molecular level of what water looks like as a solid, as a liquid, and as a gas. You can draw water as just a little circle. Okay, so take a second and draw a picture of water. Give me a pencil when you're done. I mean, a pencil draw when you're done. Don't give me your pencil. Okay. In 5, 4, 3, 2, 1. Okay, if you have, I'll kind of describe, obviously it could vary slightly from this, but general idea. Okay, so something as a solid at the molecular level, what does it look like?
Uniform.
Uniform, what else? Dense, close together, pretty much it. Right, so as long as you drew your circles close together, you can have a smiley face. You got the right idea. Now, something that's hard to draw in a 2D picture, but is important to recognize in real life, do water molecules have movement when they are frozen? Yes, they do. Say it again.
Just like very little.
Yes. What we'd say is they don't have a lot of transitional or translational movement, like forward, back, up, down, right? They're not really doing that, but they are vibrating, right? Even in this table right now, we can see the molecules, they're moving, just to the point that we can't tell. There is a point in science at which scientists say molecules stop moving, and that is known as the temperature of absolute zero, which is 0 degrees Kelvin. The Kelvin scale was built off that fact of temperature is really a measurement of movement. That's what it is. And so when you get down to 0 Kelvin, they stop moving. To give you kind of some reference, I just looked up, I can't remember the exact. In Fahrenheit, 0 Kelvin is like negative 459 degrees.
Ooh, that's a nice temperature.
Yeah. So obviously very, very extreme. It doesn't happen in nature, right? Even in like outer space, it's not even that cold. They have actually achieved it in a lab setting, which is crazy because like 10 years ago they thought it was it was just a theoretical thing. But once again, that's kind of the way you should think about temperature is about movement. Okay? Okay, water or liquids. How do liquids look at the molecular level? What's the difference?
There's no structure.
Good, no definite structure, right? It can change very easily. I heard someone say like it takes the shape of its container. Quite a bit of movement, so if you drew your circles a little bit more spread out, have another smiley face, you're correct. Yeah?
But I was thinking that the solid being more spread out is water expands when it freezes. It's like when it goes into a solid form.
I guess, good point, let me clarify in terms of spread out in terms of movement, like they're moving, but in terms of like space to space, you are right, water is unique in that sense that it gets more spread out as a solid. But in terms of they can move past each other in the liquid form, right? So yeah, if you drew it that way, then you are still correct. So okay, and then gases. How do gases behave?
They fill the space of the empty.
Fill the space way spread out from each other, very, very far. It's actually pretty crazy if we can see or take all the gas in this room. Okay, so if we were to vacuum all the gas, suck it all up, you could fit it into a box about the size of a ceiling tile and 1 foot in depth. That's how much empty space is actually in this room. Is all of it could fit in that little box. But it's crazy because gases are always spreading out, so it's not like you walk around space, right, and like hit dry patches of air. That'd be weird, right? Like you're just walking and you're like, lost oxygen in this bubble. But it just fills, so for us, it feels like it's everywhere. But actually at the molecular view, it's actually very, very spread out, okay? So unit 3, we are really diving into the chemistry of solids, liquids, and gases. Understanding how they behave at the molecular level, and then connecting it to our level. This bridge right here is super important to understanding Unit 3. Understanding, okay, what's happening at this level, and how does that connect to what we see happen. Today, and somewhat next time, we're focused primarily on solids and liquids, and then we'll transition into gases. For the solids and liquids, there's really no, just the way it's set up for the AP curriculum, it's very all visual things and explaining. The gases brings in a little bit more of a mathematics side to things. But the first part is a very visual sense of what we want to do, okay? So let's go ahead and start with solids, and then we'll get into liquids. So on that note, one more smiley face question. Discuss with your table buddy and answer this question for me as best you can. Why do you think water would exist as a solid at room temperature?
Liquid.
Well, thank you. Liquid, where am I living? As a liquid at room temperature, while carbon dioxide exists as a gas. So turn to your table buddy, have a quick discussion with them of why this might be. Why would water be a liquid and something else be a gas at the exact same temperature? Go.
I would say probably because they have different. I don't know. I have more to do with water would be an ionic bond because water would just pretty much. No.
Wait, no.
I just it's just a
Oh yeah, that's
It's got to be something to do with how strong the bond is. And carbon dioxide must have a weaker bond so that it breaks apart easier. To evaporate and then have this change.
Okay, anyone willing to share their thoughts on this question? Yeah, Landon, let's hear it.
Carbon dioxide has lower freezing and boiling point than water.
That would be a true statement. That it boils at a much lower temperature, so it already turns into a gas. Now I want to take that and add the sentence of why. Why is that? Why do they have a lower boiling point? But great point, have a smiley face for that. Max.
So we're thinking that maybe it's because water molecules are polar and they attract each other more than carbon dioxide molecules might. There's an idea, but I don't know.
That's a great idea. Zach, do you want to be a similar idea or different?
I was gonna say that carbon dioxide, the bonds between them are like weaker, so it's easier to break them apart.
Let's put those two together and that's pretty much it. Right, so I want you to change your perspective, how's my face both of you by the way, of what a solid versus a liquid versus a gas is. Okay? The only difference between them is how close they are. Like literally, if we were molecules, we could become a solid by coming together. We become a gas by going apart. So the reason why something exists as a gas or as a liquid or a solid is by how close the molecules are. Now, if there's something that's going to pull the molecules together, like polarity, then it's more prone to being a liquid versus something that doesn't, and it's more prone to being a gas. So as we talk about these things, keep in mind that the difference, once again, don't think so much hot and cold. Hot and cold don't work well in chemistry because it's so relative, right? Really, it's about movement and distance. The closer they are, the more like a solid it is. The farther away they are, or the more movement they have, the more like a gas, okay? So let's talk about our 4 types of solids that we have. These first 2 should be a review from last unit, or in a sense, review for the test even. Okay, first in general, we can visualize solids as being formed by packing a large number of small identical units. They can pack in 2 different ways. You can get a crystalline solid, where they're very uniform, or you can have an amorphous solid where it's not as uniform how they pack. Kind of depends on the shape of which one you get. Yeah, and then,
What's like an example of both of them?
water would actually be amorphous, and we'll see that here when we play with our cups of water in a second,
Okay.
because it doesn't form, once again, like a very structured.
Mhm.
Salt, on the other hand, like NaCl, is very crystalline, or typically all ionics are, because they line up in those positive and negative sheets, right?
Okay.
So, does that help you with the visual a little bit?
Yeah.
Great question. Okay, so let's talk about metals. We've talked about this before, but let's review it. So metals as a solid at the molecular level look like this, right? It's the idea of that electron C, the communism of the electrons everybody shares with everybody. Okay? We're not going to write them all down because you have them in Unit 2, but just to get our brains thinking at the molecular level, can someone remind me what was one of the properties when we did our unknown bonding lab of metals? Yeah, Taylor.
Malleable,
And why are they malleable?
because like the electrons like don't care where they go.
Yeah. I mean, this picture looks malleable, right? It looks like you could easily move it and everybody's still being balanced, right? Malleable. Good. Evan, did you have another property?
I was gonna say malleable, but doesn't it conduct energy?
Good. Yep, they're very good conductors. Do you remember why that is?
Because of the flow, like the sea of electrons.
Yeah. Things conduct because electrons move. Well, metals are very good at allowing electrons to move. So good. Have a smile, please. Stop. Let's get one more property. Someone else have another thing to think of? Yeah, Bryce.
They didn't really melt.
Good. They have pretty high melting points, right? Do you remember why that is, Bryce?
Well, it's again looking at the electron C because it like you can't really break up the bonds because it's just bonded to whatever.
Yeah, because to cause this to melt, you're literally having to break the bond, right? So you need a lot of energy to pull that apart. So good, have a smiley face back. Taylor, have a smiley face, by the way, if I didn't say that for your answer. Okay, metals, that's what they look like. At room temperature, most metals are solid. There's only one metal at room temperature that's a liquid, and that's mercury. All the rest are solid because of the force that's holding them together. Okay? Ionics are also all solid at room temperature because of this positive-negative crystal lattice that we talked about before. Okay, I'm going to pass out our cups of water. The rule is you play with them when I say to play. When I say stop, you gotta take hands off. If you can't, then I'm gonna take them away. I can't have you getting distracted with your water when I need you to be listening. Everyone understand? Now, I did not clean these from last class period. So, did I give you hand sanitizer when you came in?
Yes.
Yes. Okay, so good. Just remember, get hand sanitizer before you leave, right? Because someone else touched these water. It's dirty water. Just kidding. It's pretty good. Okay, we're gonna. So just, I have 6 cups, so we're just gonna kind of share with those around us. So YouTube can share. YouTube can share. You 4 share. Max, is that for you 3?
Oh, it's not like little.
Thought I was literally giving you a cup of water. Okay, open up your cup of water and pull out your pieces.
This is
Kind of like spread out the water between if there's more of you so everyone can kind of feel it.
green water.
This isn't water. Hey, look. They don't attract polarity and that stuff.
Okay. Okay, everybody find for me your little green and blue circle. Okay, the little green and blue circle. Okay, this right here, everybody, this is an ionic molecule. So it's showing the positive and the negative of a salt. So imagine if we took all of yours, can I go over yours here? Right? This is how we could make, can I steal yours too? Okay, so look at this for a second, everybody. So here's your salt crystal forming, right? So that's what salt is. It's positive, negative in all directions, okay? Can someone remind us of one of our properties of salts or ionic substances? Yeah, Katie. Good, yeah, they always are. They always have that crystal shape, right? That crystal lattice. And that's the positive, negative. Good, have some ideas for that. Matt.
They have high melting points.
Good, they all have relatively high melting points. Why is that, Matt?
The structure and the bonds, I think, like, it's hard to different parts.
Because to get it to melt, take your blue and green, right? You have to pull those apart, or you have to put in enough energy for them to pull apart, which it takes a lot of energy to do so, especially if you imagine it's not just a 1 and 1 you're splitting, right? But you got like positive and negatives on all sides. Okay, what's another property of ionics? Yeah, Harley. Very good. That's my good stuff. Okay, take the water, which are the little red ones, your little Mickey Mouses. Okay, and notice how the water interacts with the green and blue circles. What do we notice?
I'm not sure what the gradient is,
Okay, so take it, everyone eyes up here for a sec. Okay, give me your eyes this way. Alright, so we talked about this, but here's like a visual for you to see. The reason why ionic substances can dissolve is because the water behaves like a magnet and can interact and pull apart the two pieces from each other. Now notice that the white is sticking to the green and the red is sticking to the blue because the opposites of positive and negative to one another. Right? It's never going to happen where the white sticks to the blue because they're both positive. Okay? Alright, there's our ionic substances. Oh, someone built it wrong.
This is a red dot.
The blue one sticks to the light, but what's not as strong.
It doesn't stick if you try to actually do like the magnet part.
Oh, but if you like, because it can, oh, interest, Oh, that's tricky. But yeah, you can't stick the actual little like dot on them. So what? Oh, that's interesting. You can't truly have just a positive magnet. That's what I have. No, you guys are clever. Smarter than the water kids. Okay, everyone, hands off the water. Hands off. We'll come back to it in just a second, okay? Okay, so there's metallics. Those are ionics. Now there's two types of covalent solids. Okay? We have covalent substances that are deemed as molecular solids. So if you want to make a little side note, these are covalents. And majority of covalents are molecular solids. What makes something a molecular solid is you have a bunch of individual molecules held together by other forces, but not held together by bond to bond. Like it's not a chemical bond. This picture is not the greatest, especially maybe in yours in black and white, but what you have going on here is this right here is a carbon dioxide. This right here is also a carbon dioxide. A molecular solid is a bunch of individual molecules held together by what is known as an intermolecular force. An intermolecular force is a force between two separate molecules. It's the little force that you can play with your water, right? This is an intermolecular force. Water is a molecular solid when it turns to ice because of that force holding it together. Okay? The difference between the other type of covalent is the other type is known as a covalent network solid. Covalent network solids exist as atoms being held together by a very large network of covalent bonds. Bonding in, think of like bonding in like all directions, giant connections. That's why it's called a network. Okay? This right here is a molecular view of diamonds. Diamond is a covalent network solid. So these little black ones are carbon, and you have bonds here and there and there and there, and then forward and backwards in all directions. So instead of being like CO2, 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 it's just one vast bonding network. That's why diamonds are so strong and hard, is because you have this bonding in all directions. What's kind of cool is graphite, that's what this picture is of. Graphite is also considered a covalent network, but it's a little bit different. It's a covalent network on this flat plane. So take a look, take your pencil everybody, if you have a pencil, if not stare at your neighbors. Okay, we're gonna pretend magic school bus here. Okay, so if we can zoom in to your pencil, which we call lead, which isn't lead, it's graphite, right? The way your pencil writes is your pencil is layers of graphite on top of each other. Very, very, very thin layers. So when you take your pencil and you push down on your paper and pull a line, what you're doing is literally like laying the graphite down.
That's kind of awesome.
That makes sense? It is pretty cool. Each individual sheet is extremely strong because that's a covalent network. But sheet to sheet, so like what is very weak, which is why it just comes off when you push. Now this is where chemistry is so crazy and so amazing. Graphite, so your pencil, is the exact same atom as what's in a diamond. Chemically, exact same. They're both pure carbon. So what's the difference?
The shape.
The shape, right? The shape of it changes everything. Fun fact, because we're made up of a lot of carbon. Do you know that, right? Most living things are. If you so desire, I don't know how much it costs, but when you die, you can send in your ashes to a company and they'll turn you into diamonds.
Wait, really? I need to do that. That probably costs a lot of money.
Probably. Because it's carbon, right? and diamonds are just carbon. Obviously, it just takes a lot of heat and pressure to get it tapped out.
How much of like one person, like how big of a diamond is that?
I don't know.
Let's test it.
It was like so much. Like, it's not gonna be like my entire body. Like a 6
Yeah, you wouldn't be that big. You're not gonna be like a diamond human, right? Like an X-Man guy. And you have lots of other stuff inside of you besides carbon, right? I don't know. I guess it would be. Not to be like gruesome, but you think of like how much space the ashes take up when you burn someone. I mean, I've never done it, but at least the urns don't look very big, right? I don't know. I'll have to look into that. There's actually like, they did some funny things, like they turned a peanut butter sandwich into a diamond.
What? So you're saying
I wanna
a peanut
eat
butter
that.
sandwich could be rich?
If you could turn it into a diamond. And that's why it's funny when you think about like, when you think of things at the molecular level, it's kind of funny sometimes of why are diamonds so expensive? It's the same exact thing as what's in your pencil, right? At the molecular level at least. But so, questions on the difference between a molecular solid and a covalent network solid. Pretty much for now, the way you'd be given a picture of what it looks like to know. There's very few covalent networks. Majority are solids, molecular solids, meaning molecules and then a bunch of them. Okay, let's dive more into this force between two different things, which is known as an intermolecular force. Okay, hands off the water for a second. I'll let you play with it here in a moment. I know it's really cool. I was gonna be funny and like pour it out on the desk and then put up a sign that says like caution wet and see if any of you get it when you walked in, but or like on the floor or something.
That was super funny.
Like, watch out for the puddle. I should do it in the hallway and just see who gets in and who's like what. Okay, so intermolecular force means a force between two different things. Think of it as the friendship force between two molecules. An intramolecular force is the actual bond itself. Intramolecular forces are way stronger than intermolecular forces, but it still does exist. Okay, and it still causes a lot of things to happen. Okay? Few key things, and we'll talk about our three types. First off, what we're trying to do here between today and next time is make a connection between these forces and their properties, just like what we did with metallics and ionics, right? Of explaining, oh, well, this is why they have high melting points. We want to do the same thing with our covalent substances here. Keep in mind that it goes back to a Coulombic force. What are the two factors that affect a Coulombic force?
Distance and strength.
Thank you. Have a smiley face, Taylor. Okay? The closer they are, the stronger the forces can be. And the stronger the force, obviously, or the magnitude is the other way we phrased it, the stronger it's going to be. Okay? But keep in mind, kind of end goal is to be able to connect and explain things that we see, their properties, down to what's happening at the molecular level. Okay, three classifications of intermolecular forces. Side note, IMF is the abbreviation for intermolecular force. So when you see IMFs, that's what I'm talking about. Okay, first type of force is known as a dipole-dipole force. Okay, a dipole-dipole force is where you have a polar molecule. What does it mean if a molecule is polar? Good, so there's our picture up there. It means it has a negative end and a positive end. Because of that, it can attract to another molecule's negative or positive side. Okay, grab your little waters and feel that force. right? So that force between the white of one and the red of the other, that is a dipole-dipole force. Because the white is positive and the red is negative. Okay? Now, the stronger the dipole moment, the stronger the force can be. Now, what we mean about this dipole moment is how strongly the electrons are being pulled. Or in a sense, going back to electronegativity. Okay, so for example, let's compare like this. So if I have hydrogen fluoride, and this one, who has a higher electronegativity, fluorine or chlorine? Fluorine. So I'm going to draw two different arrows, two different sizes, just to prove a point. So since fluorine has a higher electronegativity, it has a greater dipole moment than this one, which would result in a stronger dipole to dipole force. Now keep in mind, the reason why it's dipole to dipole is it's always a comparison of one to another. This is the dipole force. The force between two individual molecules, not within it. Because by itself it only has a dipole force, but you have to have dipole to another dipole. Okay, here's a data table to kind of show that as well. So here's a bunch of substances. They have pretty similar molecular weights, but we can see the connection here between the higher dipole moment results in a much higher boiling point. Okay, the stronger the forces, equal higher boiling points. Makes sense, right? Because the tighter the magnets hold, the more energy it takes to break them apart. This is what we want to get very comfortable with. This is how the AP test is going to give it to you. They're going to give you data, and you have to justify the data based on what's happening at the molecular level. Questions on the dipole-dipole force. What it is, how it happens. Okay, second type of force is known as the London dispersion force, or we just call it the dispersion force. This is a weaker version of the dipole. So it's not a dipole, but it has a positive and negative field. Okay, here's how this force works, okay? Pretend with me right now, everybody. We won't do it because it might get a little chaotic, but pretend that we're a molecule, okay? And you're all electrons inside this molecule. What do electrons do inside atoms and molecules? They orbit and move around, right? So imagine all of you stood up and started moving around the room, right? And I just said freeze. At the moment I say freeze, is there a chance that there could be more of you on this side than on that side of the room?
Yes.
Right? Probability. Well, what's the charge of electrons?
Negative.
Negative. So if there's more negatives over here than over there, you get a temporary dipole, where it's a little more negative on this side than it is on that side. Why is it only temporary and so weak? Bryce?
Because the electrons would keep on moving and
Yeah. Right, they're still moving, so they can easily just come right back this way, right? Think of like a wave, right? They just shift and goes away. So this is the weakest force, but it explains why everything eventually can become a liquid and solid, theoretically. Is because that shift can cause them, if you look at that picture up top, to be attracted to another one. You can also kind of get a domino effect, right? Imagine the students on that side of the wall are also electrons. if we all are electrons and we run to that wall, what are we gonna do to them?
You're gonna make them move.
Yeah, we're gonna make them move because they're negative as well. So you kind of get this domino effect. But just like Bryce said, there's nothing holding the electrons there, like in a polar molecule, and so it can easily be broken. Questions on the London dispersion force, like what's happening in it at the molecular level? Okay, technical terms, polarizability measures this ease at which it shifts. So the more polarizable a molecule is, the more easily electrons move from side to side, which we see a trend in weight. So we look at our data table here, the higher the weight or the heavier a molecule is, the stronger the force is. Any thoughts of why being heavy, would that make a molecule have better dispersion forces? Any thoughts of that connection of why? Yeah, Matt.
They have more like electrons and more protons, and they just have more of each. So
Yeah, it's as simple as that. Heavier things have more electrons. The more electrons you have, the more shifting that you can cause. So it's good to have a smiley face for that. It's kind of cool to see this connection with the halogen family. If you look at the halogen family, at room temperature, they exist in 3 different states. The top 2 are gases. This middle one is the liquid, and then the bottom ones are solids. All the same family. But it's because the bigger they are, the more electrons they can shift. And so these are held as solids, but these are so small, they just exist as gases already. So kind of the same thing. The noble gases actually can be solid or liquid if you get it cold enough. But for helium, in order to get helium to turn to a liquid, you have to get down to 4 Kelvin. In order to turn it to a liquid. Because it's so small. Once again, the only reason something becomes a liquid is because the molecules come together. There's nothing pulling helium together.
Can helium become a solid?
Not that scientists know of. Yeah. Weird, huh?
Yeah, that is kind of weird.
Yeah, so scientists have never gotten helium to become a solid.
Have they gotten it to become a liquid?
Yeah.
That's kind of cool.
Yeah, weird. And yeah, I mean, once again, in a lab setting, they were able to get down to that temperature, but pretty crazy. Questions on dispersion forces? Okay, so we have dipole-dipole, dispersion, and then the last one is known as a hydrogen bonding force. This is an extreme version of the dipole. So I kind of like to relate them all to the dipole because that's what they are. So we have dipole-dipole, which is in the middle. You have London, which is a temporary dipole. And then you have hydrogen, which is an extreme dipole. Now the reason why it's so extreme is for 2 reasons. Number 1, hence the name, you have to have hydrogen in your molecule. But you also have to have a hydrogen that is bonded to nitrogen, oxygen, or fluorine. I think NOF is what you have to have. You have to have a NOF sandwich to have hydrogen bonding. Here's how it works, okay? So here's our water, and this is what happens in your little water right here. So who has a higher electronegativity, oxygen or hydrogen?
Oxygen.
Oxygen, right? So water is pulling the electrons away from hydrogen. But there's something significant about pulling electrons away from hydrogen. What happens if you pull an electron away from hydrogen, Matt?
It has no electrons.
It has no electrons. So not only is this positive, but it's in a sense a bare nucleus. So it's like really positive,
It's like neutral.
which increases this force of attraction between the two. Now, it only works with nitrogen, oxygen, and fluorine because of their high electronegativities. Outside of that, it would just be classified as a dipole-dipole bond. But those three have such high electronegativities, they cause that big difference in the positive and negative force. Okay? Right up here are some examples of where you can find, if you want to like kind of maybe circle them or make sure they stand out to you, some hydrogen bonding. So all of these red dots are different examples of where hydrogen bonding exists. Notice you have to have the knock sandwich. H in the middle, N on one side, and on the other side. Same thing, H in the middle, O on one side, H on the other side. I mean, N on the other side. It wouldn't work if it doesn't have it on both sides of it. Questions on the hydrogen bond? Now, it is important to know, and I didn't come up with the name, so don't blame me, but it's not a real bond. I don't know why they named it a hydrogen bond. It's not an actual bond, but it is pretty strong. So what I want you to do is, with your little water molecules here, sometimes it helps just to touch and feel things. I want you to come up with a scientific explanation of why it hurts to belly flop. Ready, set, go. Talk to your table buddy about it, and then we'll share.
Oh, maybe it's like how ours are like the surface of the water, and like you have to break all the hydrogen bonds to make water.
Oh, wait, because since the hydrogen bonds are really strong too, it's not just like
Yeah. Because these hydrogen bonds.
So like to move the water, because if the water's flat, to move the water, you have to break all the hydrogen bonds. And that's a lot of force.
Okay, anyone want to share their scientific reasoning? I guess I should have specified related to chemistry, not physics. Of what? Okay, Isaac, let's hear it.
So the water molecules are all connected a little bit, and so then to break a little bit, it's not really hard. So if you just like if your feet going first, it's not very hard. But if you belly flop, it's more surface area on it, so it's more bond holding together, so it's hard to break it. And
Yeah.
you just hit it.
That's how strong the hydrogen bonds are, is they can hurt, right, if you hit them the right way. I imagine it as like the water is playing like a game of Red Rover against you when you jump into it, right? And if you don't hit it the right way, then you feel that force. Has anyone ever been up to Park City in the summertime and watched the ski jumpers do tricks into the pool? Some people have been there. You know, it's really cool. I don't know if it's happening because of COVID, but maybe next summer. For someone who has gone, what do they do to the water?
They like bubble it.
Yeah. So the ski jumpers are like doing tricks off jumps into a swimming pool. But what they do is they break up the surface tension by shooting jets underneath. If you break up the surface tension, you can hit the water however you want and it won't hurt. Or at least not hurt very much. It's kind of a similar idea of like using a foam pit for like gymnasts or skateboarders, of how it breaks up that tension of it. So you
Do
have
they
to
do that for like diving at Olympics too?
yeah, like when they're practicing. Yeah, because otherwise, like, that would suck to, like, belly flop all the time.
Yes.
I mean, and technically that's why it's illegal to jump from certain heights at Lake Powell, is because it's deadly, right? From certain heights, water can kill you if you hit it the wrong way. I mean, I had a friend who got a black eye from wakeboarding one time, and it wasn't from the board, it was from the water. You know, because it...
Crashing wakeboarding hurts so bad.
Yeah, it can.
It hurts so
You
bad.
crash a few times and you're like, okay, get me back on the boat, I'm done. At least that's how I feel. So, questions on the hydrogen bond? Okay, one more. Isaac, have 2 smiley faces for sharing and your answer. If you had something along the lines of Isaac in your discussion, you can have a smiley face as well. Okay, let's fill in this table and then have a little demonstration to keep us thinking here. So this is kind of summarizing all 3 forces just together so we can kind of compare them.
No one will even assume that cat races, so that's a good thing, I guess.
Okay, so our 3 forces, once again, we have dipole forces, dipole, dipole, London dispersion, and hydrogen bonding. All 3 forces are about positive and negative forces. Now, once again, just to make sure you understand, molecules are not magnetic. But this force is like a magnet, which is why we can use these to visualize it. Okay, but water's not a magnet, right? You stick up water, it's not magnetic. But it behaves in that positive and negative sense because of those Coulombic forces. Okay, we have our permanent dipole, temporary dipole, and extreme dipole. Now these forces are additive because everything that has electrons has dispersion forces. So in water right here, a water molecule has dispersion forces because it has electrons that can shift. But on top of its dispersion forces, it also has dipole-dipole forces, as well as also hydrogen bonding forces. So it's not like it has only one, they can be additive on top of each other and have multiple, which once again can increase the strength of them. Yeah, Isaac.
What is the top right corner?
Oh, closer. I know, it gets really hard to read when it's up there. So it's strong when the molecules are closer to each other. Once again, you take your little waters, right, the closer you put the waters together, the stronger they can feel that force. So. Okay, this is water, by the way. I filled it up from my tap if you didn't see. Okay, this is oil. Using your little model sets and with your table buddy, I want you to come up with an explanation of what you see happening here. Okay, so I want you to explain with your table buddy, why do oil and water not mix? Ready, go.
Yeah, so maybe like water wants to hydrogen.
This little guy can symbolically represent oil, by the way.
Okay.
It's not old.
Spilling oil all over.
What atom is oil made out of?
Say that again. Carbon and hydrogen.
I think.
Okay, first thing, a lot of students would say, and maybe you said too, when I do this, they say, oh, oil's less dense than water. Is that true? It is. Yeah, that's why it's floating. But is that why they don't mix? No. To give you an example, alcohol and water, those mix and they have different densities. Max?
Is it because oil is extremely non-polar, and so maybe just the water isn't attracted to it at all, so it just separates?
And say that phrase one more time, that last sentence.
The
was
water
perfect.
isn't attracted to the oil at all.
The other thing, a very common wrong saying that people also say with oil and water is they say it repels. What does it mean to repel with forces? Push away. There's no pushing away happening. What's happening is the water isn't attracted to it. It's attracted to itself. Water would rather hang out with itself than it would with the oil, so so they just stay separate. Great explanation, Max. How does mine fix
Wait,
that?
so does oil like have surface tension?
Ooh, you tell me.
Take the off of yourself.
Yeah, like,
Yeah, let's do it. Really pop it.
I think no.
No, this is something I've always wanted to try, and I wanted to send into Mythbusters before they went away. So, yes, it would have a surface tension because it does have dispersion forces. But in compared to water,
Yeah, not very much.
so I need someone with a swimming pool who wouldn't mind us filling it up with oil. And we can test this.
I need a swimming pool.
Because, right, like it has less surface tension, so theoretically, it shouldn't
As much.
hurt as much, right? Be pretty messy afterwards. But. Okay, next part of the demonstration. Everyone watch this, ready?
Oil, that would be nasty.
Okay, so after this I want you to, so once again, explain to me what you see happening, ready? Alright, everyone, bring your eyes up here. Watch carefully. This is food coloring, by the way, because you know.
No.
Oh,
No. Wait.
oh.
That's kind of so.
So turn to your table, buddy, and explain to them what just happened at the molecular level. Go.
Why did that just
Well, so clearly the food coloring doesn't want to mix with the oil.
I think the oil is
So the coloring bodies isn't attracted to the oil. It is attracted to the water. So it attracts to the water, goes into the water.
that is so weird.
Here's your substance. The oil just this is the food color, just like.
Okay, I think I heard it in a variety of different ways, but what does this demonstration tell me about the forces of food coloring, Harley? It must be polar, right? Because it's mixed with the water. It had forces similar to it, so it could interact. Versus, what did it do in the oil?
Straight
It hung to itself, right? It formed these cute little spheres, right? Because it's latching to itself. That's why I couldn't find any, but they actually have like,
Oil food coloring?
yeah, it's not called that, but you use it for like candy, like chocolate. Because if you try to color white chocolate, it doesn't work with normal food coloring because it's a difference of properties. You have to buy a non-polar food coloring so it can interact with it. Pretty cool, huh? Questions so far? Yeah.
So if you had non-polar food coloring, and you put in water, would it just do like the same
Yeah,
thing?
it would just stay as like a little sphere. Yep. Yeah, pretty cool, huh? Any other questions? Oh, yeah, smiley face for the explanation, by the way. Yeah, Max.
Just wondering, how high could you jump into a pool of water if it didn't have the surface tension? Like if there were like jets floating up the
Yeah.
water, how like,
What's the highest you could go from and still be okay?
yeah,
I don't know.
because people say like,
What happened to lab?
jumping from a high place into water is like, just like feel like concrete if you're high enough.
Yeah.
But like, if the
'Cause it's a surface tension.
is like not there,
So if you take I mean, theoretically, this is me just hypothesizing, right? Like, because if you break up the surface tension, then in a sense it's just like the water molecules are just like catching you, right? Now you are still going to feel some sort of
And you'd
force.
probably go pretty deep too.
That's the thing, you would go pretty darn deep. I wonder how deep that
What
pool
if you
is
go
at Park
so
City.
deep that you die of no air before you get out?
I don't know.
Yes.
Huh, we're gonna have to combine our forces with the AP Physics class and figure that out.
Would the stress from your body stop and kill you though? Because you're going so fast.
That's what I don't know either. Yeah, like I don't know if, even though the surface tension is gone, you're still hitting stuff, like matter, right? So that, like what force, but it is like moving matter, so it like cushions you, right? I don't
If you
know.
go deep enough, there's enough force on top of you.
And that's the other problem too. You have to go too deep, then you're gonna have other problems just because you're so deep. We'd have to tie something around you so we could pull you up really quick.
Or like a
figures that out later.
Just how high can Max jump? That's what we want to know. I don't know. What think about that? That's an intriguing question.
So how come like submarines can't go super like deep into the ocean? Like what is that? Like the water like
The water pressure.
just like
There's like so much weight underneath.
Yeah, it's just because of the weight, right? Because it's matter, right? Even though we can go between it, it's still piling up. And so eventually that pressure just gets too high that it just crushes the. We'll actually bring that question up again when we talk about kind of gases. And I'll do a little demonstration with a can in water, and that will kind of show it a little bit. But great question. Any other questions right now? Okay, the last thing we need to be able to do, kind of our objective, is we need to be able to, given a structure, you should be able to say, oh, that thing has these forces. Now, it is important to recognize some overlap here. Generally, dispersion is the weakest, and hydrogen bond is the strongest. But you do have this overlap region of where some forces of dispersion are stronger than some forces of dipole. Now, this crossover error isn't like something you have to memorize. But if they give you data saying, hey, this molecule has a higher boiling point than this one, the data always proves the forces. Meaning if something has a higher boiling point, its forces must be stronger than the other substance. Okay, hydrogen though is pretty much always the highest, but notice the big jump, especially in the numbers. Okay, this is intermolecular forces. These are actual bonds. And the scale, it's not to scale. Right? To break the actual bond itself, or in a sense to take the ear off of Mickey, that takes a lot of force. Right? It can be done. You dig your fingernails in there and put them together because they came in pieces. But it takes a lot of force to do so. So that's the difference between a true bond and an intermolecular force. Chemically speaking, to do this, you normally send electricity through water. If you send electricity through water, you can break the hydrogens off the oxygen.
So I was trying this on for twice. I was like, it's like,
Okay, go to this last table here, everybody, and let's wrap up with this.
it would hit the highest thing, and water's like really close.
Okay, make some labels. Okay, these three columns right here, okay, are intermolecular forces. Intermolecular forces only happen within covalent molecular solids. So if you want to kind of like put a little label, bubble around these, that these three are only for covalent molecular solids. If something is ionic, it doesn't have intermolecular forces. Same thing, if something is metallic, it doesn't have intermolecular forces. It just has metallic bonding and ionic bonding. So these ones, so the first question when you have to identify something is to first ask the question, is this ionic, covalent, or metallic? First question you should ask. So, NH3, is it ionic, covalent, or metallic?
Covalent.
Good, how do you know that, Taylor?
Because it has 3 hydrogens and 1 nitrogen, and when the nitrogen bonds the 3 hydrogens, it doesn't generally make ionic because you can just have 2 things. No, but yeah.
There you go, he's getting there. Right? I saw a lot of you looking at the periodic table, you look if it's a metal, if it's a non-metal, right? Since these are all non-metals, it's a covalent bond. Since it's covalent, the next question is, okay, is it a covalent network? 99% of the time the answer is no. I'll tell you the few times it is, but pretty much it's not. Which means it fits in these 3 categories. How do I know if something has London forces? Someone said it, I couldn't quite go with Matt. Matt, what'd you say?
Because all of them.
Yep, so this is always yes. If it's covalent, it always has London. Okay? How do I know if something has dipole forces?
Basically like Shakespeare.
Carly?
It's like, if she has the ball run around the room.
Good, we have to look at its structure and see, does it have a positive and negative side? Meaning you have to draw its Lewis structure if you don't know what it looks like.
So like, if you're all.
Okay, so I'll draw it right here. So it looks like this. Okay, so give me a thumbs up. Is that structure polar or not polar? What do you think? Thumbs up polar, thumbs down non-polar. And if you need more help with this before you take the Unit 2 test, please reach out. The answer is it is polar. What about this structure makes it polar? Or why is it polar, Bryce?
Well, if you look, nitrogen's gonna be pulling all of the electrons into it, so the two hydrogens that are across from each other would cancel out because it's the same pole, but then the other hydrogen on the bottom doesn't have anything to cancel it out, so it tends to be.
Good, and he's on the right track. He's a little off in the structure actually because of 3D space, but that's how you determine polarity, is you look at which way is it pulling and do they cancel each other out. This one technically is actually the pyramidal shape, so they're all pointed like this, which in a sense then there's like nothing to cancel any of them out, but you're on the right track, so have a smiley face back. So since it is polar, yes, it does have dipole-dipole forces. All polar things experience dipole-dipole. How do I know if it has hydrogen bonding? What am I looking for?
Hydrogen and hydrogen.
Good, hydrogen attached to a, that works. There we go. Questions so far?
So like if it's an oxygen connected, or like oxygen, nitrogen, or fluorine connected to a hydrogen, will it always have all three?
Are you saying like if it has hydrogen bonding, will it always have the other ones?
Yes.
Pretty much.
Okay.
Don't quote me, there could be an exception to that. But I would say generally yes, if something has hydrogen bonding, it's going to experience dipole forces and then always has limited forces. So, yeah, good connection, Taylor. Okay, krypton. Now keep in mind, we're talking about forces between. So we're talking about if a krypton comes in contact with another krypton, what forces does it feel? So first off, is that ionic, covalent, or metallic?
That's none of them. Is it?
Is krypton a metal or a non-metal?
That's a no.
So two non-metals make what type of bond? Or force? Covalent. Okay, so then what type of force does it feel? Always lemon. Oh, hey, thanks. Just what I wanted. Anything else?
Dipole, no.
No.
Because they're
Nope. It is not polar because it's just a single atom. No hydrogen bonding. And if it has these, it never is going to have those.
oh.
Okay, let's skip down just to prove a point. So let's come down to KMNO4. What type of bond is KMNO4? Ionic, covalent, or metallic?
Ion.
Yes, it's ionic. So, since it's ionic, it just has ionic bonds. We'll practice this more next time, but there is going to be, I'd rather write this down. Just a little quiz on Canvas to practice this, just so I can see how we're doing. But we'll go over it more next time, okay? Biggest thing to remember is to take that Unit 2 test tomorrow, okay? And then this for lab is due by Friday. If you could clean up your water for me and put it in the cup real quick, that would be awesome, just so I don't lose any pieces. Oh, no. See, it's pretty cool water, right?
Water tracks to metal.
I'm pretty excited about it. Oh my gosh, this is
You just have like